Yeah, so first of all, thank you for the organizers. Thank you for Deb, for Lizmart, for Park. Really, this is a long relationship with Park, and I'm happy to be part of this symposium, 2021 Latin America, and appreciate the introduction as well. So I'm a professor at the University of Tennessee at Oak Ridge National Lab. I'm a staff scientist, and formerly I was professor and am still actually a professor with Case Western Reserve University. So the area of research we do is in interfacial chemistry, different types of nanostructuring, use of patterning, surface-sensitive methods like the AFM, QCM, XPS is standard in our fair. We do synthesize a lot of materials. And in fact, I'll show you some of the polymer materials that we have focused through the years. I'm also the editor-in-chief of MRS Communications Materials Research Society. So I do covet your best contributions if you're interested as research letters or prospective articles. So as I mentioned, we synthesize a lot of materials. We focus a lot of work on conjugated, biconjugated polymer materials, dendrimers, ladder polymers, black copolymers. Recently, we have done a lot of work on what we call supramolecularly templated Knotty polymers. This involves the use of supramolecular templates like phenanthrulene that is complex with, let's say, a metal like copper to force the formation of catenated and knotty structures, resulting in very high or high molecular weight polymers, supramolecular polymers. Another specialization in our group is the grafting of polymers and surfaces using surface-initiated polymerization, and this can be done by crafting the density of initiators or various types of polymer surfaces to enable RAF, ATRP, and other types of living polymerization methods. We've done a lot of work on nanostructuring of layer by layer deposit polyelectrolytes and self-assembly of nanoparticles. This allows us to rapidly form thin, ultra-thin films that have various compositions, layer order, and dense functionality. And then lastly, we have done a lot of work on what we call hybrid dendrimer materials. These are macromolecules with different types of core, including inorganic and metallic cores, where we emphasize on charge transfer, electron transfer mechanisms to define their functionality as gas host systems, sensors, or even thermal therapy components in plant viruses. So let me start in terms of nanopatterning, electropatterning by emphasizing the role of conducting polymers. So even now, conducting or conjugated polymers are used a lot for developing sensors, different types of actuating devices, even bulk heterojunction, solar cells or LEDs. And so this type of material is very important to us. Even 10, 20 years ago, we have utilized these conducting polymers and string them with other component polymers in what they call precursor polymer cross-linking approach in order to cross-link films that are electroactive, optically active on substrate surfaces. So for example, we can take, let's say, polyvinyl carbazole and cross-link them at the engine tin oxide surface to enable the formation of an LED diode with polyfluorine as shown here, where the cross-linking of the PVK and the oxidation state can control their efficiency or even turn on voltage. So what I'm talking about is pictorially depicted here. So engine tin oxide is a transparent substrate conducting because of the engine tin oxide layer. You can see that this is a very rough layer by AFM. But by grafting the initiators, AIB and LAG, and grafting polyvinyl carbazole or polymer brush, you can see a smoothening of the surface, again by AFM, as shown here. Now, not only do we smooth the morphology, we can actually use this to improve the performance of devices, as in this case with an LED device using, again, polyfluorine and cross-linked PVK. The resultant polymer grafting gave us lower turn-on voltages. Or in this case of this photovoltaic device, involving that of, again, a grafted polyvinyl carbazole using a CTA or RAF polymerization to graft the polymer brush. We then prepared a device, a bulk heterojunction cell device made up of polythiophene and PCBM. The result is we got an efficient device with the PVK brush grafted on the surface, similar to what we would have gotten with a PDOT PSS whole transport material, as compared to an ITO without this grafted device. So we were stable. We were able to demonstrate the stability on flat surfaces, device fabrication. We then turned on to patterning. So as you can see here, there are many levels and directions for patterning, including lithographic and non-lithographic methods. Certainly, AFM plays a very important role because this allows us to use, let's say, a cantilever tip or conducting AFM to deliver the molecules, or in our case, to actually pattern the oxidation or electropolymerization of the material. So we first noticed this phenomena in microstructured patterns, let's say these self-assembled monolayer dot patterns, where we actually formed micro LEDs based on the patterning of a carbazole modified polyfluorine, as shown here, where we electropolymerize the polymer, or precursor polymer rather, on the dot structures, resulting in this micro LEDs and IV performance. Now we then are able to transform this into a nanopatterning strategy by using actually conducting AFM tip, where the bias voltage can be passed between a conducting substrate and a conducting tip. So this bias voltage actually delivers enough to cause Joule heating or to cause electropolymerization. We can have a negative or a positive voltage bias, which in turn results in an electropolymerization of, let's say, that PVK monomer that I showed earlier. Now, this strategy was employed in a number of demonstration devices where we can vary the voltage or current, we can vary the speed of writing, and therefore change the feature sizes of the nano pattern. These are basically 100 nanometer or less pattern, where we can also use lines, different geometric shapes, and actually use this to demonstrate a type of memory device that was patterned by the AFM. Now, in terms of polymer synthesis strategies, we did make a lot of new polymers that can be patterned this way. Corresponding here is that of a polyelectrolyte, polycation and polyanion, polyvinyl pyridine and polyacrylic acid, bearing a carbazole electropolymerized monomer. Now, we can deposit this as thin films, alternating between the negative and positively charged layer, which can be monitored by the increase in absorption over this UVB spectra. And this project was actually done by two of my graduate students at that time, single graduate students, Cheng-Yu Wang and Gochan Zhao. So Gochan and Cheng-Yu worked together, where Cheng-Yu synthesized these polymers and prepared the films, and Gochan studied the electro-patterning. So here you can see the electrochemical behavior. We can cross-link this at about 0.6 volt initiation, resulting in cross-link films of several cycles with defined current or voltages. Now, nanopatterning is easy. What we simply do is we move the AFM tip, conducting AFM tip, and then wherever it moves, it electropolymerizes the film. So we were able to make different line patterns, different shapes, different heights based on changing the bias voltage or changing the number of layers or changing the writing speed. And one day, when I went to the lab, I noticed that Gotchan made this heart shape, okay? And I asked him, well, why did you make a heart shape? Well, he said, I like a heart shape in contrast to a normal square or straight pattern. And so I noticed that they have been working quite late, both of them, several weeks. And then finally, they told me the real story. They were getting married. So this is actually a work by Gotchan and Jiang, which was published eventually as a cover page in Macromolecules. And they got married. So there's a real love story for you. So let me turn to the next patterning strategy. We use non-lithographic electrochemical patterning using colloidal templates. These templates are essentially monolayers of polystyrene that we deposit using a Langmuir-Blodgett deposition method. We will then electropolymerize through the interstitial spaces and then digest or remove the polystyrene or template and resulting in an array pattern. So this is how the colloidal particles look like when we first deposit. And then after electropolymerizing through it and then removing the particle template, this is what we get. So depending on the current or the voltage, you can have potential static or um, galvanostatic, potential static or control or changing current. We can get a half dome, full dome structure. We can even remove these particles by delaminating it from the surface. So using this templating strategy, we were able to demonstrate that you can make conducting polymer arrays by varying the type of initiation and the monomer that was used. Here, we demonstrated the deposition of a conducting polycarbazole through these polystyrene patterns, resulting in an array of this conducting polymer, and again, monitoring the deposition by CV, or a cyclic voltammetry. Now, what we have in the middle are basically blank spaces of the substrate. This exposed area of the substrate can be grafted with an ATRP initiator, and then you can grow a polymer brush, in this case, polynipam, so that you get a polymer brush within those conducting patterns as shown here. Now, to visualize the difference between the conducting pattern and the non-conducting polymer brush, we were able to use a conducting AFM or current sensing AFM to distinguish between the IV current on the conducting pattern colored green and the non-conducting polymer brush colored blue. So this is one of a good way to combine electrochemical information with AFM. In other cases, we demonstrated that the patterning can be done where the electropolymerization actually occurs on the pattern, not on the holes. So in this case, we electrodeposited an ATRP, a raft, and a metathesis initiator. After grafting the initiators on the surface, you get this pattern in the middle. And then after growing the polymer brush, you can see the brush formation on top of the pattern. And again, of course, since we still have a hole in the middle, we can backfill that. And then we can create a pattern within a pattern or a polymer brush within a polymer brush, as shown here. The grafting of the ATRP initiator was done by silane assembly on the ITO substrate. Now, we did try to mediate the control of the electrolyte passage through these brushes. So this is a sort of a membrane demonstration where we can monitor the membrane transport through the exit and entry of ions on the brush. And therefore, the thicker the brush, which is exhibited here by a 6R polymerization, prevented transport, whereas a bare ITO, you can see the in and out of the hexafluorophosphate ions. I think iron cut ion to the substrate surface, resulting in a higher current density. Now, another way that we utilize these patterns is to demonstrate molecular imprinting. Molecular imprinting is a method of producing an enzyme-like activity where the lock and key mechanism was demonstrated by using a template molecule, and in our case, using electropolymerizable monomer complex of this monomer and analyte, and then electrodepositing them on a quartz crystal microbalance surface. After depositing, we would remove the template and we should be left with an array structure similar to before. So the AFM here again confirmed the formation of this patterned array, hopefully with the cavities of the original template molecule embedded on those arrays. And the reason for that is we utilize this for sensing. So the sensing activity was monitored by quartz crystal microbalance experiments. The norepinephrine minus and plus are really enantiomers of each other, where one a type of norepinephrine is actually the active drug and the other not. And what this shows is that we can switch between the sensitivity towards one enantiomer over the other simply by varying the template. The decrease in frequency means that you have binding or high binding kinetics of the analyte on the original template, which was exhibited by the MIP, but not with the NIP or non-imprinted polymer film. Moreover, when we did the selective or competitive binding, naproxen or dopamine, which were not the original template, did not bind on the surface, but only the original template. And lastly, solvent washing with application of a potential or voltage results in a more efficient sensor as one without it. And then finally, showing to you the extension of our work, we used actually plant viruses. Now, these are not coronaviruses. They look like, but they're really plant viruses based on the cowpea mosaic virus analog. We then functionalize or can functionalize them with dendrons, as I showed earlier, or do grafting of polymer brushes. And in fact, we have utilized this to template the adsorption or grafting of DOTA and chelation of platinum ions, which can be perhaps used for photodynamic anti-cancer therapy. But I won't focus on the this work with the phototherapy, but rather show you that we can take those viruses like this and then pattern them on colloids. So these are the TEM images of the viruses, and then pattern them on colloids similar to what we did before. In this case, the viruses are going to deposit on the ring structures or the arrays that are shown here, and then we were able to remove them in terms of their grafting structure. And so here are the templates, and here are the viruses surrounding these templates, and we were able to remove them as freestanding films out of the original substrate. So with that, I'd like to thank you, and I'll be happy to answer any questions you may have.